Good morning, everyone. Hope all the participants are doing fine. I see there are 36 participants already, and I think we should get started. Yeah, Barbara has indicated that I can just get started. I'll start my presentation. First, let me make it in full screen. And then can you all see my presentation in the full screen mode?
Yes, it's perfect.
Yeah, I'm audible, I guess. Good. Let me start with a brief introduction. I'm Raghavendra Ashrit, can all call me Raghu, and I work at the National Center for Medium Range Weather Forecasting that you see in the background. So we are the Medium Range Weather Prediction Center, and we work behind the official Met Agency. Official Met Agency in India is India Meteorological Department. We provide all the number crunching services, modeling activities, scientific R&D associated with the NWP-based forecasting systems for medium range, short range, and also extended range up to seasonal prediction, not beyond seasonal. So we are a supercomputer center with forecasting models running for short range, medium range, and extended range. We have a coupled system used for extended and seasonal range type of prediction. My area of interest is forecast verification, severe weather, and post-processing. And so we work with deterministic as well as ensemble models, test different post-processing methods and bias correction techniques to improve the forecast for different applications. So today my focus of interest is verification methods for rare and severe and extreme type of events. Focus will be mainly on extreme rain. It can further be translated into other parameters also. So in addition to extreme rain, I touch upon verification for tropical cyclones, verification methods that are in practice for tropical cyclones as recommended by the WMO guidelines. So I'll get started and let me know if my slides are not moving or if any technical glitch is happening. Please let me know. Otherwise, I will not have a way of finding out what's being seen. So this is a broad outline of my presentation. I have divided into two sections. First part is the verification for rare and extreme events. I give some examples and discuss the statistical scores, their statistical properties and things like that. And second part is for severe weather. I have chosen the tropical cyclone track forecast and verification methods. I was thinking to include visibility verification as well as lightning, but then I thought that wouldn't be possible to accommodate within the stipulated time. So I just thought we'll stick to just the two of these. I'm going to my next slide. And here is an incident. It's like probably participants from India will identify very well. So in 2005, there was a very big deluge in Mumbai, and you had 944 millimeters of rain in 24 hours. Okay, and as you can see from the bottom panel, like climatological long period average rainfall that is shown for the month of July is just around 850 millimeters or so. So this is the climatological average. And this was a case like a significant portion of your seasonal total rainfall is received in one day. and this is a record highest rainfall anywhere in India, single day, one single day rainfall. You have another example from Saudi Arabia. This is also an interesting one. This was from 2017. And as indicated in the bottom left, you can clearly see 63 millimeters of rainfall in 24 hours in one place, and in a nearby place, 90 millimeters in 24 hours. And as it can be seen on from the right, like this is 3 months of rain in 24 hours. This was one situation. So typically, these are the types of events which shatter the records, and we start thinking like, is it an extreme? Do we call it an extreme anomaly, or what is it? How it can be called? How to understand this? So, what is an extreme event? A definition often used in statistics is like extreme events are the events which lie in the tails of the distribution. So there are other ways of definitions here, as they can be indicated. You can just indicate based on the highest and the lowest values. And if we have a highest on record maximum temperature or the lowest on record minimum temperature, then we can call that an extreme. So it can be just based on the magnitudes, like the highest 3-day total rainfall, highest weekly rainfall, and things like that. Or it could be in terms of the rarity, frequency. Such an event never happened in my lifetime. You will often hear old people talking about it, like, I have never seen such an event in my lifetime. I have never seen a tornado, something like this, never in my lifetime. Not so frequent, never so frequent, like that. So some people express, and we can understand the extremes in terms of rarity also, how rare they occur. Or they can happen in terms of severity of the impact. This is a little bit of a tricky issue, because probably severity of the impact could be exacerbated due to many other reasons, but by and large, still severity can also be thought of to indicate and try and see if it was an extreme event. Especially in case of monsoon, it is like that any number of methods could be used to establish what represents an extreme one-day event in highly variable climate types existing across India. So in variable climates, like such as in India, it becomes very, very difficult. Like there could be different definitions for different regions. To explain the same in the context of climate and climate change, the graphic on the right hand side clearly shows the temperature distribution. The bell curve is what is seen here, and typically the types of changes that are introduced by climate change is either in the form of a shift in the mean that's shown in the top panel, which also affects changes in the record hot weather events near the tails, or shift in the variance that is shown in the middle panel, where also again, like, the tails of the distribution are disturbed, and you have record new hot and cold conditions. Or it could be both, shift in the mean as well as variance. Even in that case, there could be serious changes, and we can have new extremes that can be thought of. And as per the WMO guidelines, based on the country survey, there are specific definitions, and WMO comes out with two specific ways of identifying the extremes. For precipitations, extreme precipitation events, I have just indicated with a square rectangular red box here. A precipitation event is considered extreme when it exceeds certain threshold that has certain associated impacts. So if we can have a definition based on a certain threshold, like 50 centimeters in a day or things like that. Or it could be like a precipitation event is considered to be extreme due to its rarity. So it could be based percentile based. So a rare event like can have like something that exceeds 90th percentile or 95th percentile. So that could be another method of identifying. This is rather more practical, and it is usable across different climatologies. So many metrics and many verification measures also use this as one of the ways of identifying the extreme too. Uh, verify as well as forecast. And just to summarize, what we can say is extreme events bring severe impacts to life and property, and they are very rare, unexpected, unprepared, and underprepared to cope and manage with the impacts. And we definitely need forecasts. Now we have high spatial and temporal resolution forecasts, and definitely it is expected that they predict severe weather and also predict extreme rains with severe impacts. And also we know very well that in the 21st century, in fact 20th century also showed increasing trends in the extreme rains in India and also in different parts of the world. And 21st century projections also indicate increase in the intensity of extreme events. So all this makes it very important that extremes need to be addressed, studied, verified, and things like that. But there are huge challenges. Basically, observational data, very high resolution, high quality controlled observational data is still like a challenge when we want to identify and study when the extreme events happen in a very sporadic manner in very isolated locations. So that becomes a very challenge, and it takes years of analysis and further gathering of evidence to actually classify something as an extreme event. Next is the sample size. Generally, these events are rare and they will always come with small sample size, and there is a lot of uncertainty. And if we try to have a data pooling in space and time, that can introduce inhomogeneities and you give rise to different kinds of problems. So they are characterized by very large values, and sometimes they can be like seen as outliers and removed from routine studies. And so it is also need for robust and resistant statistics that are necessary for the treatment. So there is a whole lot of branch of statistics called extreme value analysis, which helps us to uh, study the extremes in weather and climate. Also, I will not touch upon the topic. I have not been like not an expert on in-depth analysis of extreme value analysis, although I'm very much interested. Now, the interesting part that we are focusing on is the verification scores. Suppose if we have, assuming we have an ability to predict, and how do we verify? Is it possible to verify the extremes? That is what we will try to see. So I'm trying to start with a graph here that shows the daily precipitation over Mumbai. Okay, this is the data during June to September monsoon season. So I have just taken the monsoon season rainfall from 71 years. So starting from 1950 to 2020. So every September I end and I start with next year, June. So what I've shown is the daily rainfall, daily accumulated precipitation. So in India, the standard practice is to accumulated rainfall during 3 UTC to 3 UTCs, uh, 1 day rainfall. So this is from the station located in Mumbai, Santa Cruz. This has a long record for nearly a century, and that shows like nice uh, episodes here. Like we can see every now and then we have rainfall exceeding the 99th percentile. So the climatological 90th percentile is something around 81 millimeters. 95th percentile is 116 millimeters. You can see it on the right side. And the 99th percentile is 209 millimeters. So there are events like very like not very rare, but still they are like once in a while, like every season, every 2 or 3 seasons, we do get to see these events. And there stands the tallest one that happened in 2005, which we saw in the first few slides. And this is the kind of variability that we see, and this is the kind of rainfall amount is what we see here. It's huge amount of rainfall. It rains almost all days during the season. So there is like huge amount of persistence and things like that. And for the present analysis, I'm trying to avoid all the big shocks and just confining to a small period of 8 years, 2013 to 2020. For this period, I have taken 8 seasons for which I have model forecasts from my center, NCUM. This is the NCMRWF Unified Model. Okay, so NCMRWF Unified Model forecast rainfall I have taken here. What I'm showing here is the average day one forecast for each season. So I'm not providing a comparison with observations here. That's not the aim. Just to highlight for all other participants who are not familiar with the geography. So this is typically how the monsoon rainfall over India looks. You have, if you can see my cursor, on the west coast, you have large amount of rainfall every year. This is where you have a lot of mountains. And on the northeast, you have a lot of mountains and you have large rainfall amounts. This is very much comparable and it's almost all the years you will have. Apart from that is you have over central India. This is the central plains where you have a lot of rainfall activity associated with the low pressure systems. So during the monsoon, you have low pressure systems, which even sometimes intensify into deep depressions. There is a tropical storm and make inland and they travel across the northwest direction and bring in a lot of rainfall activity over central India. So the west coast, central India, and the northeast, these are the rainfall hotspots. Apart from that, I can say, like if you can look at 2014, the eastern part of the peninsula is relatively dry, and the northwestern part of India is again relatively dry. So this is typically how the monsoon looks. Anyway, for today's discussion, our focus of interest is the city of Mumbai, which is located on the western coast. I'll just zoom in and show here the gray backgrounds that you can see. This is the mega city of Mumbai. It's also a peninsula surrounded by Arabian Sea, and you have inland waters, and there are several water bodies and things like that. And you have mountains here. So the impact of mountains and strong southwesterly monsoon current brings in a lot of rains and many heavy rain spells during the season. So this is our region of interest. With just we can go ahead and see how typically the observation and forecasts compare. So I have just picked observed rainfall over Santa Cruz, located in Mumbai from 2013 to 2020 season. And the top panel shows the observations. And here also you see in the last 8 years, there have been occasions where like the rainfall has exceeded 200 millimeters, more than 100 millimeters quite often. And similarly in the forecast, day one forecast, if I just look at, and here also we get to see like the model forecasts quite often exceed 100 millimeter mark, and also sometimes the 200 millimeter mark. So this is how it compares, and we can clearly see model has tendency to produce big rains, which are common in observations. The bottom panel shows the scatter plot, showing a comparison. There are a large number of false alarms that, as we can see, and also there are several missed events, as we can see from the scatter plot. In addition to that, in between, we do have some of the events which show some positive association. That is what we can come up with this type of forecast. So this may not be a very perfect case, but still I thought it would be interesting because we have a lot of extremes in observation as well as the forecast. Now, in total, I have 8 seasons and 122 days. That amounts to about 976 is the sample size. There are a few missing values, but not very huge. Just if we go ahead, and I have applied, before we carry out any further analysis, I tried to apply calibration for the forecast so that we have the mean bias eliminated, and we will have an opportunity to study Yeah, so this is how like the calibrated forecast. I'm showing it on the right side panel. Rank based empirical probabilities are shown here, and we can clearly see that the probability is largest for extreme rainfall. If you see the right top corner, we can clearly see there is some dependency near the extremes. So next, going ahead, I'm using the calibrated forecast to carry out categorical verification scores, which were discussed by Marian 2 days ago. And just like this is the contingency table elements, I compute the counts of hits, misses, false alarms, and correct negatives. And from that, I can compute the hit rate, frequency bias, false alarm rate, and P gives the base rate for my data set. And as it is demonstrated in some of the early studies that most of these verification scores, when I extend like as base rate indicated here in the top axis, as base rate approaches zero, the verification metrics, magnitude of these metrics become very diminishingly low. Very so. This is what specifically this is shown for hit rate and false alarm rate, and yeah, hit rate is decaying much slowly with increasing rainfall thresholds, but false alarm rate is decaying much faster. But both of them approach zero as the base rate is decreasing. Similarly, for critical success index as well as heat case score, I show here like we can clearly see that even for the 90th percentile, if I want to have, which is my 80 millimeters rainfall, I clearly don't have any skill in prediction. Like it doesn't show any like good verification score. Similarly, for equitable threat score as well as uh, PSS. So we have diminished low values, and this is a demerit with some of the standard verification metrics, and this is the challenge. Like verification measures change, the properties change as we move towards the rare events. Hit rates and fall alarm rate, they decrease towards zero, and this happens mainly because the elements of contingency table, uh, hits, misses, and false alarms A, B, C, they tend to decay towards zero, but they are decaying at an unequal rate. Thus, verification of extreme weather events, now it's a challenge, and we definitely need different types of approach and different methodologies to do that. So, following this, uh, some early study by Stephenson suggested expressing the contingency elements in terms of the hit rate and false alarm rates. So this is how it goes. I'll just quickly, yeah. So that you're going to make your counts independent of the base rate. All elements are expressed as a function of H, P, and F, so that your counts can be, you can design base rate independent measure. So first one proposed was extreme dependence score, and this is defined by logarithm of P minus logarithm of H divided by logarithm of P plus logarithm of H, where P is your base rate, H is the hit rate. And this verification measure is called the extreme dependency score, and it summarizes the performance of deterministic forecasts for rare binary events. And the property of EDS is that it converges to a meaningful limit rather than asymptotic limit. And it is for unbiased samples, it is reliable indicator of the skill. So if we have bias corrected samples, then it's a very good measure for assessing the skill for predicting extreme type of rains and rare type of events. However, it is inequitable, and for random forecasts that overpredict occurrences, like this score rewards by high expected score. An equitable measure is like it is desirable and it should assess the performance relative to random forecasting systems. So there is a revision and there is further uh, suggestion by another study, Hogan, in 2009, where in place of the base rate, Q is suggested. Q is the frequency of forecast events, and this verification metric can be applied to uncalibrated forecasts while retaining the same desirable properties. And it is found that SEDS and EDS, they are like they are equal if P and Q are equal for calibrated forecasts, and SEDS is higher than EDS if Q is greater than P. And however, still SEDS is still base rate dependent. It's non-regular. There are some of the undesirable properties which are discussed in FERO 2011. And the present metrics that are recommended and widely used are extremal dependence index and symmetric extremal dependence index. So these are the two indices. I'll briefly touch upon what is the difference and how they can be uh, understood. And they have the same properties as EDI, and including logarithmic of 1 minus f and log 1 minus f terms merely makes SEDI complement symmetric. This is also discussed in earlier this thing. So expressing the same performance of my forecast using EDI and SCDI, we can see here that even for my thresholds exceeding my 80th percentile, which was 80 millimeters, 90th percentile, which was 116 millimeters, and so on, like I still have the magnitudes of the score very much like non-diminishing and like very constant around zero 0.4 or zero 0.5. Both EDI and SCDI are non-vanishing measures of association. They have meaningful values. They can be very good measures of skill for predicting EDI. I'll just quickly go ahead and see if time permits, I'll discuss. FERO 2011 provides a very detailed in-depth analysis of each and every metric here. I will not read through all of them, but it is good to know like how EDI and CDI metrics. I have made notes here, so like you can read them and clearly indicate it is indicate the benefits over other earlier metrics is clearly indicated here. I'll quickly just skip some of this discussion. Yeah, and see like these metrics are now widely used. This is what I can show from ECMWF report. On the left side is sedimetric for extreme wind when exceeding 98th percentile, shown as change from earlier period. So it shows sedimetric in the form of a trend. And similarly for 24-hour precipitation, for rainfall exceeding 90th percentile, and how the metric has been changing over reference time. And a similar study we also carried out to show the improved performance of Metaphys forecasts over India, with specific focus on the West Coast mountainous regions and the Northeast India, the mountainous regions. We had access to Metaphys forecast rainfall from 2007, and we could clearly see the improved skill in terms of the verification that is shown here up to 2018. This study, of course, it's time to update further. And in addition to that, we also have odds ratio. Odds ratio is also a very good, useful metric for, specially suited for verifying extreme weather. Odds ratio is just, it can be understood as ratio of odds of a yes forecast being correct to odds of a yes forecast being wrong. So it measures the ratio of odds of making a hit to odds of making a false alarm. So this is greater than 1 when the hit rate exceeds the false alarm rate. So it has a logarithmic form of expression also that can also be, it gives a better score for rare events. It is less sensitive to hedging. Only precaution is that this should not be used when if one or more elements of the contingency table are equal to 0. The log of odds ratio takes the range of minus infinity to plus infinity, and 0 indicates no skill, and perfect score is anything, it's infinity. So both for the case of Mumbai, we can clearly see for higher rainfall thresholds which are of interest, we clearly see like increasing score. So clearly indicating model has some skill at higher rainfall thresholds, that is indicated, and this could be another metric for assessing the extreme values. This is again odds ratio skill score, not specifically for extreme events per se, but this is much more general. It ranges from 0 to 1, and it assess performs, it gives what is the improvement of the forecast over random chance. So these are some of the references that could be very useful for in-depth understanding of the scores that we were discussing. And I quickly give a summary of what we discussed so far. We touched upon what are the best scores for extreme events like EDS and odds ratio, EDI, CDI, odd ratio, some of them, and we also saw how they perform against the traditional metrics. And can the rare event scores be improved by hedging? Yeah, definitely. For all the traditional metrics, like, you have to be very careful. They are sensitive to hedging and base rate. And how much skill is there in extreme weather forecast? It appears like by using some uh, of the metrics, odds ratio, and these family of scores of EDI, we can say that there is quite a bit of skill, and that could be useful. And that's it. And I should I take a break and say questions now, or complete, Barbara, complete the talk? Let me know if I.
I think you can go on, and if people have questions, they will put
Yeah,
them in the chat.
yeah,
But it's
yeah,
up to you.
yeah,
It's up to you.
yeah. In the next part, I'm right now, I'm not seeing the chat box. That's why I just asked. So for tropical cyclones, track and intensity are very important, and they determine the level of devastation and severe impacts. So accurate prediction of track and assessment of track errors is very crucial, although it sounds very simple in practice. But for operational purpose, track forecast is very crucial, and that determines all the decisions relating to disaster management and associated activities. So on the right hand side, you can see a graphic showing the uh, forecast track in gray color, and you can say observed track. This is actually from the first case, but yeah, to understand, like, this is the observed track in black. So track error typically constitutes distance between the observed position and the forecast position at a particular valid time. So in this particular case, 36 hours after you start your forecast, the observed position was somewhere here, much to the northeast of forecast position. Okay, this is at 36 hours after the starting of the forecast, and at 36-hour lead time, my predicted position of the cyclone is here. So the distance between these two positions is shown in purple, and it's called as direct position error. Direct position error. And along with direct position error, you can also decompose it in components of cross track error, that is the perpendicular distance between the two observed and forecast track, and along track error, that is along the direction of movement. What is the error along the direction of the movement? So these two components determine the forecast performance, and that is how it's briefly discussed about how these computations are made. Now, the forecast track error is defined as the great circle distance between tropical cyclone forecast center position and the best track position at the verifying time. So these two positions, like in real time, you will not be able to do it because the best track position is something which comes much after, like few days after the cyclone has made landfall and things like that. So it's essentially a post facto exercise to monitor the model performance and things like that. So for description of the procedure, geometrically it is shown here. The green, like the OB1 and OB2 are the two positions of observed cyclone. So OB2 is the current position, right? And forecast position is here. So the distance between these two is my direct position error. Okay. And this is obtained as the great circle distance. And great circle distance is uh, important for in meteorology and many other sciences to account for curvature of Earth when you measure distance between the 2 points. And it is computed just by like taking the latitude longitude values from the observed position and latitude longitude positions from the forecast positions, and use it in this formula and convert it, and direct position error is available in terms of kilometers. It could be 100 kilometers, 300 kilometers, or 500 kilometers, depending on your forecast lead time. So this is an important quantity that clearly tells how good your forecast tracks are and how fast the forecast track error is growing with lead time. Depending on that, the official forecasters issuing the forecast to different disaster agencies and all, they can take a call on if the forecast errors are traditionally known to be very high at 5-day lead time and 3-day lead time, they can account for those biases. At shorter lead time, of course, they can keep monitoring and take a decision about if the forecasts are reasonably really good, and they can clearly um, announce that the cyclone will be tracking towards such and such location, or it will make landfall between those cities and things like that. So all said and done, this is a simple exercise, but it could be very challenging for some of the looping cyclones, tracks cyclones that make multiples of recurvature and things like that. So then the direct position error, sometimes they go haywire and zigzag. There is no systematic increase in error with lead time. That's what happens. Now discussing about the components of the direct position error, we need to compute the cross track error, that is a perpendicular distance between the forecast position and the observed track. So what is done, it's a simple exercise, like just the observed position, present position, and the past positions are extrapolated to intersect the line from forecast position. So you just construct two intersecting lines, perpendicular intersecting lines, and then using basic coordinate geometry, the position, intersecting positions can be computed. So if that position, intersecting position is computed, you know the cross track error, direct positions, direct distance between these 2 points gives you cross track error. So once you know direct position error and the cross track error, uh, uh, along track error can also be easily calculated. So, how the convention is, if the cross track error is positive, the forecast position, it is understood the forecast position is to the right of observed track in the northern hemisphere, and it's to the left of observed track in the southern hemisphere. So consistently, if your models are producing this type of errors, so that it's like can identify that the model has the left bias or the right type of bias. And similarly, if cross track error is negative, yeah, it has left of the observed track in the northern hemisphere and right in the southern hemisphere. So now this is again valid for cyclones which have not yet recurved, and once if they are moving, recurving and looping, then you will always have difficulty in uh, understanding them, and you can only interpret in such a positive CTE would indicate that the model has a poleward bias. Whether it's northern hemisphere or southern hemisphere, you can say it has a poleward bias. So just to showcase, like generally these computations are made, and for any tropical cyclone case, you aggregate the values for all the days. If the cyclone lasts for 10 days and you are making like twice daily, then there are 20 samples and things like that. And then you have uh, the errors demarcated at lead forecast lead time, direct position error, along track error, cross track error. So these are all in absolute quantities to show the magnitude of the error. Similarly, based on the same concepts, you can also get the landfall position errors. You can pick and choose the exact position in the forecast where the landfall has occurred. Based on that, you can also identify the time error. So whether it was making a landfall early or late, forecast landfall is early or late. And similarly, aggregating such scores, it is possible to showcase like how your landfall point error, whether it has decreased over the years or whether it has increased or not at different lead times, whether it has decreased or not. That type of a thing can be indicated in a graph like this. Similarly for landfall time error. So all these help in making a case for asking for money, improving the infrastructure, buying more radars, buying a new supercomputer, and things like that. So that's how it goes. And just to touch upon intensity, intensity is expressed in terms of mean absolute error in minimum sea level pressure and mean absolute error in maximum sustained wind intensity. And that they can be computed for each forecast, and then the values can be aggregated and shown like this. As you can see with forecast lead time, the errors keep increasing, and some, like, it's rarely, this is one single case where you can see the magnitudes going up and down, but when the values are aggregated over several cyclones and several years, so they you can clearly see a systematic growth of error. So for intensity, so generally what happens is sometimes the cyclones have like they weaken very fast, they die over sea, and generally there is a possibility of miss or false alarms that can also happen. And sometimes the like the models may produce TCs which don't exist at all, so they there are also false alarms. So these also happen. So it is possible to have identify the hits and misses, put them in terms of the contingency table, and also you can uh, get the verification scores like false alarms, probability of detection, and things like that for to quantify model biases and show their intensity tendencies. So similarly, for you can also verify intensity tendency, like if the forecast change the intensity in successive lead times, and if the observations also indicate intensification, so that's sort of a hit, like, right? So model is predicting the observed changes in the intensity. When the model is predicting a strengthening or it's weakening and your observations show otherwise, then it's a miss. Okay, this way you can get the elements of the contingency table, and finally come for can get the hit rate and express the intensity tendency in terms of intensity tendency skill scores. And this is related to random forecast. And here is an example. If we have around 80 hits and 20 misses, the hit rate comes to around 0.8, and the intensity tendency skill score comes to around 0.6. Okay, so we can say that the model scored 60% more than the random chance. And in the other case, if like there are large number of miss, only 40 hits and large number of miss, then your intensity tendency skill score is very bad. It comes to about zero point 0.2. You can say your this particular model is it's worse than the random chance. So if the intensity tendency skill score is greater than 0, the forecast shows some skill in forecasting the intensity tendency. So when we have, if you go for mesoscale models, designing highly high resolution mesoscale models, justifying that like global models don't capture the intensity of the cyclones very well, and we want to have mesoscale models running. And this is the way it is possible to test if your mesoscale models are doing the good job, and this is what intensity tendency skill score should be greater than 0, and that should be the target. That's all. So these are some of the important references for tropical cyclone uh, track verification, intensity verification. Similarly, there are some more metrics which are useful, but that could be enough for the present discussion. I thought I have exceeded my time, or I don't know. I'll stop here, and I'll be happy to take questions if there are any. I'll stop.
Thank you, Raghu. You haven't exceeded your time. You're good.
Yeah, now I can see the time.
Yeah. Okay. So at the beginning, the questions are always a bit slow, but I think I saw one very early. Shimelis had a question. Do you want to speak up, Shimelis, please?
Okay, can I speak now?
Yes.
That's good. For short range forecasts, we will say prediction or projection. Which word we will use it as a scientific person or as a profession, and why?
Yeah, for short range, medium range, and seasonal, anything in the range of up to seasonal or even multi-seasonal, you can say it is always forecast, because you are being very definitive about when. Okay, so projection is much more vague. So multi-decadal scale, if you are making any prediction, then you can call it a projection. You're not specific about any period, early part of next century or latter part of it's a very broad. So projection is very broad. So in climate scale, you can always use the word projection, or in any other forecast time scale, you can always use the word forecast. Forecast or prediction, they are one and the same.
This means they are synonymy, forecast and prediction.
Yes.
That's good. Thank you.
Just on a lighter note, if I can add,